In this video, we're going to talk about one of the first basic steps for using your body as a model to understand structural behavior, called body structures or the sort of feel of things. So you probably, in fact, know, I'll start with this sort of thesis. Whether you've had any experience in building structures at all, you probably know more about structural design than you'd expect. We have talked about this importance of getting over the idea that structural design is somehow difficult to learn. Our bodies, in my opinion, are the fastest way to get over this. Learning structures may seem difficult or complicated, but it does not have to be. Profound lessons about structural principles can be felt and understood simply by being mindful about what our bodies can teach us, or, as I contend, what they've already taught us. Our bodies anticipate and adjust to the different structural conditions we face daily through the trial and error of just living, walking, sleeping, standing, carrying, lifting, all structural principles. Throughout our lives, we've subconsciously learned to design our body into responsive and effective structural forms. It's easier to carry something closer to one's body when it's heavy than it is to take it and lift it high up and over and out. Why? It's a simple structural experience, right? The trials and errors of our physical experiences have prepared us to already connect with what we feel and that what we'll try to learn. By enacting particular poses in a mindful way, and then recording the results of what we see and feel and doing that, and lifting things and moving things and balancing things, what we end up recognizing is that there are certain principles involved that intuitively we already understand, and that those things are foundational to structural design. By tapping into those, we have a foundation of knowledge and a reliable learning tool to be able to assist in our design efforts. That's how we can make body structures into something that's an actionable learning method. Your body, as you now know, can create and test structural solutions, and it can do so quickly. You can make simultaneously adjustments of different variables, span, length, etc., and evaluate the three-dimensional consequences of these changes. Look at these diagrams. Consider how or why these poses feel different from each other. Which ones do you think would be easier than others? And then consider what would the resulting form be that was created in doing so. In other words, make the connection between stresses and physical form. Once you do so, you'll understand there's this inescapable relationship between the structural form and the type and the location and the magnitude of the stresses. What do I mean by that? Again, consider these particular poses. In which ones do the arms hurt? In which ones do the abdomen hurt the most? In which ones is it easier to hold it for a longer amount of time? If it's easier to resist those loads, then perhaps the type and location and magnitude of those stresses is optimized in a way. Once you start to think of these, therefore, that certain structural forms can be created by you to be responsive to different conditions. Where do these structural solutions come from then? We had argued previously that it's intuitive. It comes from an experience. We'd also argued that we didn't have to wait for calculations in order to be able to come up with what these solutions could be. All true, completely valid. Here's the thing though, that's not all there is to it. Structures is a science. It is based on principles of physics and mathematics and material behavior. So we have to be well versed in those basic principles too in order to design and then evaluate our work. We should be able to use our body structures to learn the terminology that you must know and the concepts behind the principles that you must understand in order to be a structural designer. Let's start with some basics. How do structures stand up? Structures, of course, rely on a supporting frame and a foundation to be strong enough and stiff enough to resist the forces acting upon that. As we'll see, this is a combination of both external and internal support systems. What we're looking for is static equilibrium. A static structure is one that is not moving. Equilibrium means that the sum of all the forces acting upon the structure equals zero. All the vertical forces and all the horizontal forces equal zero. So when we look at a static structure, this structure isn't moving. There's two different ways of thinking about equilibrium. One is translational, up and down. The other is rotational, side to side, front back, or spinning in plan. All of those, of course, have to be static. A deeper dive into translational equilibrium. So there's two ways of thinking about this, and these diagrams are a way of being able to show the different ways of maintaining translational equilibrium. One is an equilibrium with the external resistance or support systems. In this case, the external support system would be the ground. This ground is able to support that body. It's an equilibrium. Or if it's not and you sink down, that's no longer an equilibrium. Right? So there's an external resistance. There's also an internal resistance. If our body is indeed a structure, we need to make sure that the actual elements of our body structure are able to support the weight. So for instance, if the knees buckled or the ankles buckled or the legs just simply weren't strong enough, it's not a problem with the external, it's a problem with the internal resistance to forces. Another way of thinking about this external and internal resistance to forces has to do with rotational equilibrium. In this case, what we see is the rotational of side to side or front to back can be an external condition. In this case, there's a bull on one side and a person on the other, and depending on the length of the particular lever, we might be able to find a way that they could have equilibrium. But in this case, it doesn't look like it, right? The bull is too heavy, rotating down, so it's the external condition of the loads and supports that doesn't work. There's also an internal capacity to resist overturning stress as well. If this person's trying to hold a whole nother person out at arm's length, we know there's a great deal of stress on that particular shoulder joint right there, which is going to make it quite unlikely that overturning moment can be resisted. Force vectors, it's important that we understand that these are graphic representations of magnitude, in other words, the amount of force, the direction, where the force is acting, and sense, which means is it compressing, is it pushing, is it pulling, the direction that happens. So a sense is the force acting on or away from a point? An angle has to do with the direction of it. And now this is a really important concept we'll always keep coming back to. The arrow length is a graphic representation of force magnitude. Therefore, force A is drawn with a length of x. Force A has a sense that it is compressing this particular point. If force B is twice the amount of magnitude, we would draw it twice as long as force A. Therefore, because we know that forces have a magnitude and the magnitude is represented in the length of the arrow, this allows us to do really simple basic things like be able to demonstrate how much weight a smaller child is versus a cat versus a larger person versus a bull. Even if we didn't know the actual values that were listed next to it here, we'd be able to tell by the magnitude of the different arrows. Right? In this case, we know that the cat is less than the child and the adult is more than that and the bull is more than that. It's so instantly you could recognize the different weights just simply by the length of the arrows. The other important part here is we're trying to maintain equilibrium. We show that equilibrium is maintained by showing arrows that point the equal and opposite direction. Load acting down, resistance provided. Load acting down, resistance provided, etc. Now, the ground may be able to provide much more than 100 or 20 or 2,000 pounds. It's just that we know that it is providing that because they are in static equilibrium. The same can be said down here with this particular diagram. This is not an equilibrium because this person is pulling on a rope and there's no equal and opposite force. If someone is pulling the rope in the opposite direction with the same amount of magnitude, this actually is a static condition. The wall, of course, could also maintain a static equilibrium position if the person is pulling against that particular wall. Now that we've understood the importance of forces and arrows to be able to demonstrate the amount of load that's acting upon it, let's get in a little bit more detail about what these loads could actually be. What I've demonstrated before, which is simply the self-weight of either a child or a cat. Those are dead loads, right? Those are loads in which these structural elements are just sort of permanently acting downward. In this diagram, and these are sort of the basics that you'll always have to understand here, that there's three different types of loads: dead loads and live loads and environmental loads. As the diagram shows you here, dead loads are mostly static things. These are structural elements, things that are fixed, footings, the weight of the building. Live loads are things that are able to move around. These could be occupants or furniture or storage or vehicles. Environmental loads, of course, are the ways in which the wind blows and the earth shakes. It can be thermal expansion, it can be snow, ice, rain, seismic, wind. A good way of thinking about dead loads and live loads is this. If you took the building and somehow magically turned it upside down and shook it really hard, what falls out of the building would be a live load. What stays is the dead load. All of these have like code-given measures for how much certain materials are going to weigh and how much you're going to have to be able to accommodate for different types of live loads. As we begin to try to understand and diagram these arrows, there's other conventions that may help us if, again, we start to think of them as body structures. So the location of our arrows indicates the type of loading and then the type of support conditions, because remember, we're using arrows to indicate equilibrium. Think about how these diagrams could be applied to both a dead load, a live load, and environmental loading condition. I'm showing you on the left here, material weight or a dead load. We're going to imagine that this person is actually static and not able to move. We're able to show these lines that come up where the supports are. The other thing about the diagram, we're going to be able to show where the supports are. I'll line those up. This length is the span length, L. And we're able to diagram this if we know the load per unit of the span, or it's called a W. These units can be either pounds per foot or kilograms per meter, and they're a linear, uniformly distributed load across that span. What happens if a cat jumps on the back of this person? How would we re-diagram it? We know the force would be different. Well, we're going to keep the same location of where the supports are. We're going to find out where the center of gravity of that particular cat is. We know that this cat has to be diagrammed in a different way. That's a live load. So it's the dead load of the person, a live load of the cat. The live load then is going to be an arrow acting down. That arrow is a load, P, which would either be in pounds or kilograms. What if a whole bunch of small cats climbed on, right? A dead load and a uniformly distributed live load. So again, we're taking the same thing as the second one, but we're having smaller arrows, smaller arrows, smaller arrows. Each one then lines up with that particular person. In all of these scenarios then, we're able to then measure the effect of how much that load is, where the supports are, and how this can find both external and internal states of equilibrium. Think again about like how important this terminology is when we start to diagram different structural conditions as we go through here. We really want to make sure that we understand the use of the terms P for a point load, distributed load either as a W or the capital W, and then the units for each one. When it comes to force, flow, and equilibrium, think about the way that the forces are moving through one's body, but try to visualize these not necessarily at first as arrows. Think about them again, as Mario Salvadori suggests, as like the flow of water through a network of pipes. So think about diagramming the direction that this water flows and making sure that our pipes have enough capacity to hold the water. At the beginning, not much water. We start to collect it and transfer it. As the water is collected and transferred to different parts, there's more water. Transfers to another part that's bigger, that captures it more. Again, more forces, more water. But the flow is always constant. It goes downwards, right? Now, there are some structures where it pulls up, but for our visualization purposes, we're going to think about water falling down, collecting, consolidating. When we start to think about doing arrows, then we can start to have combined loads and combined support systems. Start with the basic idea that we've seen before, static equilibrium, down and up. But now we have this combined force flow. The cat to the child to the adult adds up. Force flows. Therefore, equilibrium is if all of those forces are able to be resisted. So externally, that's great. But remember, we have to have internal equilibrium as well. What happens if we have the same three, but we just reverse the order? 200 pounds down to 100, down to 20. I think this is trouble for the cat. I'm really not sure that the cat can support 300 pounds up above. This then is a problem with internal equilibrium. So while the ground may be able to support all that weight, everything that holds up the weight above has to be able to push and act opposite. So really the way you would think about this is if the person acts down and there's another arrow that goes up, this is 100 pounds acting down, this person internally must be able to provide an equal and opposite force upward. So you could diagram it as this plus this is that. This gets interesting though when force flow acts in a more complex way through a building, and again in our case through a building structure, where you might have a person and each one of their legs distributes 100 pounds. That 100 pounds rests then on a shoulder of the supporting person. That weight moves itself across and over. They then split that weight up into two different legs. Look at what we're getting here. We're actually getting this much more interesting way of thinking about how forces flow besides just a very simple diagram of down and up. And the reason that's important is because then each individual element then can be sized based on its internal role that it has to, of the support it has to provide. The legs, the shoulder, etc. So a static structure is this constant battle for equilibrium as it moves to try to move these forces and resolve the forces throughout it. So it's this struggle, it's this internal struggle, and you feel it with your body, between forces that try to push, pull, bend, and twist, all by trying to resist these particular stresses. So we can diagram these with a state of equilibrium as you sort of have two equal and opposite arrows, like it's pushed, or it's pulled, or it's bent, right? Or it's twisted. But one of the most fundamental skills is trying to understand what those arrows actually represent in terms of the stresses that they create. Stresses are what's happening within the body when these arrows are applied to it. This is terminology that you have to understand because the state of stresses has everything to do with both material behavior and overall form. Again, the body helps us to really realize this because we already intuitively and inherently understand these states of stress. Compression, pushing both sides together. We know what types of forms create compression. Tension, pulling the two sides apart. We can feel that in this particular body structure. Torsion, the twisting, the instability of this where the body wants to twist. Shear, because the shoulder really wants to sort of give up. It's passing one particle vertically past another. Or bending, the idea that you'd have compression on one side and tension on the other, all within one particular element. Those states of stress are able to be diagrammed with arrows and with force arrows. And when we can start to not only trace all the force flow through these systems, but then with the arrows, we get a much more complex and very interesting diagram of what's really happening within our structures. Consider the idea of somebody being held up by a person down below in two different scenarios. In one scenario, they're standing on the shoulders. We know that this person's body is in fact compressed. What if they're held out only by the hands on the two sides? In that case, their body is still compressed, but their arms are tensed. Those are not the same scenario. Overall, big picture, they are the same scenario because they're both in equilibrium. But if we are going to try to decide what materials, what connections, what type of structure we're actually going to create, this added complication of a load going down and being pulled back up in tension in order to be converted back then into compression would require a great deal of concentration and detail. One of the other complications when we start to understand force flow and the magnitude of all the forces has to do with what happens when we start to combine the loads. It's not just that we're trying to understand whether the bottom element could support all the weight that happens up above, but now we get into a different type of equilibrium. Translational equilibrium would be just trying to help understand whether or not this person down below could in fact hold up 500 pounds of weight up above. Fine, let's say they can. But that's not the only risk here, right? I mean, it may be an equilibrium translationally, but my guess is the idea of 5 people standing on each other's shoulders, we know that the bigger risk here is going to be rotational equilibrium. Because rotational equilibrium makes that sort of the factor that we want to be able to design against. It might actually be a question of should we be able to change the geometry to be more responsive to that load. So stability, the rotational equilibrium becomes the controlling factor. As such, the geometry has to change. Taller needs to become wider as well. We can see these in these classic body structure competitions in Spain, in which you see that they've combined themselves into different configurations that helps keep them, the taller that they stack, the more stable that they are. They've linked themselves around. They have different ways of tying themselves together. And of course, they're so worried about being tipped over, they have a whole group of people that are able to support them at the bottom to make sure that that doesn't occur. Form follows the forces. So when we think about a triangulated support here, the further apart these get, something interesting happens with the forces, the load, the arrow. This arrow, when it starts to act in a diagonal direction, has what we call two components to it, a horizontal and a vertical force component. As such, it means that it has a thrust that pushes outward. It's not just only going translational up and down. Particular geometries then have both translational and rotational that have to be resisted against. So when we look at this structure here, this sort of A-frame, what we know is the person's leg that's out here also has to have an equal and opposite diagonal force, which means that something has to be able to stop that thrust, has to be able to push in. The thrust out has to be able to be pushed in. Now think about the consequences of this when that thrust is higher and higher up. In this case, 1, 2, and then they have the same scenario. Now we have a horizontal force acting way out here. That creates, as we know, a moment force. A horizontal force times its moment arm. Form and forces can be responsive to this if, in this case, you have another element that's here that's only meant to resist that horizontal force. So it becomes wider and additional thrust resistance. Gothic churches, when they became taller and bigger and thinner. In each and every case then, as they grew taller, another element was put out to be able to resist more. In this case, imagine if there was another body here pushing again out there. So the force flow becomes down, out, down and over, and down and over and down, which allows it not only to have translational but rotational equilibrium represented within its structural elements. Once we start to inflect these dynamics of a force that's just not acting up and down, but diagonally or side to side, in other words, once we go from just translational to rotational equilibrium, we have to start thinking about vectors, their direction and magnitude in a more detailed way as well. Picture yourself enacting the scenario that's shown here. Which way would you prefer? How would you stand? Why? Think through it intuitively. Why would one of these be more effective than another? And then, especially if they're the same weight, but just a different geometry of a support. We know intuitively that we would rather have our legs underneath our body, right? But why? How can we actually use vectors and direction and magnitude of arrows to prove why this may be more effective? So again, as the reminder, a force that at an angle has both a horizontal and a vertical force component to it. So the horizontal and vertical force components. And then if this is geometry is changed, force P prime here, then the magnitude of the horizontal changes and the magnitude of the vertical changes. So the magnitude of the vectors, both horizontal and vertical, is related to the arrow length, of course, and the direction of that particular arrow. How does that help us? Well, it means that we can actually start using basic trigonometry or basic, diagrammatic functions to understand the force vectors and the length of them. How so? Let's take the diagram. Person is holding up 400 pounds. Let's only talk about vertical forces for a minute. So 200 pounds each leg, and we have a 90-degree angle. Now, let's say the person spreads their legs out, and again, we know that the vertical force is only 200 pounds. 200 pounds straight vertical because the load up above is a straight vertical force. But it has to be more than that because this has both a diagonal and then a horizontal component to it as well. If they're spread out even further at like 50-degree angle, and again, the consistent part here is the vertical force, so that force arrow has to come down all the way to the tip of this 200, but because it's at that angle, it has more of a horizontal force component. So look, no horizontal force component that's moderate, longer horizontal force component. Each time it goes from 200 pounds to more than 200 pounds to the highest amount. So each pose then we know poses greater diagonal stress in the legs. Simple math. The vertical force stays constant. The angle changes, the triangle dimensions. And so we just solve for the forces within the leg. The magnitude is what we're after. Geometry works because we've drawn these forces to scale, and therefore if we solve the triangle, the length of the different parts of the triangle, we then know what those forces would be. Let's come down to the different solution here. V is 200, right? H, this horizontal component is 54, and its overall magnitude is 210. If we come over to the one with the 50-degree angle, solve it the exact same way. Again, we know V has to be 200. This becomes 50. And now look, the magnitude of this overall has become 260. So the forces in your leg actually feel 260 pounds instead of just the 200 if they were straight up and down. Because the vectors are drawn to scale, we can reflect the magnitude and we can see it quickly. You don't have to do the math at all. Okay? You just look at the arrows and say, that arrow is longer. This is a graphic statics method that we'll get into. Another basic but important idea that has to do with forces and direction and overall configuration is something that's called a moment force. A moment force is something that I think you can understand relatively intuitively. Picture yourself doing the scenario that's shown here. You've got a weight, you hold it out as far as you can from your body. How do you feel? What do you feel? What would make this easier for you, right? Less weight, less distance away from your shoulder. Why? Well, we can describe that just by simply calling it a moment force. When forces act downward at a certain distance away from the point of support, we generate what's called a moment force. So the force, the weight, is acting downward, and it's operating a certain distance from its main support mechanism, which is the body. Therefore, it wants to tilt downward. To resist it, instead of just one arrow, we're actually showing it as a combination of arrows that would make it so we'd have to rotate back. So the weight P is being pulled down, it wants to rotate. There's no angled support, which would be great. In fact, we know that would be one easy way to resolve it, because then the arrow could just simply go straight down. But there's not. So the shoulder connection, the pin itself, has to resist this. The math is so basic. A moment force is the force times the distance. The amount of weight here times its distance. So check what you thought intuitively. Less weight held further out from your body would be easier. Yep, let's check that out. Less weight, less force, less distance. Any combination of those would actually make it easier. So the force times the distance. As that weight moves further away from the body, the greater level of stress is in fact created. Minimal distance, lowest moment. Maximum distance, highest moment. Now, this scenario doesn't happen often where we just decide to cantilever something out from one particular point of support and structures, but what we're going to find is that this principle helps us to understand how and why beams bend, and how that when a beam gets longer, there's more moment force acting within it when it bends, and therefore we can start to make other choices about our beam design. As you start to think about this idea that bodies and body structures and the configuration of bodies help us to understand forces and loads, allows us a way to visualize what's actually going on, both as an external and internal equilibrium. The idea that we have to be able to solve for equilibrium, and that we do so with arrows. Arrows show us force flow, that these arrows also help us indicate which might be the larger problem to deal with, translational or rotational equilibrium. That the arrows actually help us to figure out how different connections are put together, what connections we want to think about, whether this is the states of stress that it creates, compression, tension, torsion, bending, shear. How we can actually use basic ideas of these vectors in order to help us understand the magnitude of forces that are acting upon something, both horizontal and the vertical force components. And mostly it just gives us a sense of just trying to understand the difficulty of how structural configurations work. I'm going to show you a scenario that was acted out by a series of graduate students at Iowa State. I want you just to consider how much they learned by doing it, just by acting it out, before they then had to diagram it. They're going for the record amount here. They're leaning back. They're pulling as hard as they could. The two guys in the middle holding on as hard as they could. They eventually had to tape their hands together because they were pulled apart too much in tension. What did we learn by this? Look, pulling. One person alone couldn't generate enough thrust to be able to pull outward. So they had to have two people do it. Two different supports, right? The other thing you realize is the configuration. Look at how they're leaned back sideways. That was the easiest way for them also to generate a force that came out. They're able to resist that overturning force that wanted to pull them down and over rotationally into the middle. And of course, we see this amount of stress right here with their hands. It's the only way they could hold themselves together. Why'd they do it this way? That it was easier for their abs to be held in tension when they were face down. So very, very simple, but profound demonstrations of this idea that body structures, in fact, can tell us more about structures when we first start than we would imagine. Thanks, appreciate it. If you like what you're looking at, please subscribe. Lots more video content. Look forward to part 2 of this particular lecture, in which we're actually going to talk about how we do the 2 different exercises of how far you can span and how high you can reach. Appreciate it.